session, surprisingly online. See, so since I'm not able to carry out your meetings these days because of shortage of time, so I decided to make a video of that. And this topic is actually based on flat solar system. I know. I had earlier also carried out on the same topic, but to some point it wasn't satisfactory. So this time I have made some pictures and some corrections and explanation to make it more clear to you. So it goes as follows. As we know that in the realm of cosmos, like any other solar system, since our solar system is also flat. Okay, so earlier it was like a nebula. You can see this is a stellar nebula. Since it is the camera works on inversion principle, so these words are inverted. So I'm saying this that it's written stellar nebula. So earlier the matter was in form of cloud called stellar nebula. Okay. Later, due to the random motion of particles in the nebula, the collisions happened and caused elevation of temperature, and the chaotic and the random motion formed the superheated clump of infused matter of gas, fused matter in the center, and the whole cloud started shrinking under this gravity. Okay, so a disk of gas started shrinking and started revolving with some angular momentum equal to the overall angular momentum of the whole cloud of nebula. Okay, so actually started forming a disk. Now, how could it form a disk out of a huge cloud of dust and matter? Let me explain. This is what it formed. It's certain protostellar disk. Okay, so how did it form disk? Uh, and why not a clump of a huge ball of gas in sphere, form of a sphere? So let me take as an assumption, if in case particles start falling in the center to form a sphere, then the particle in motion having some gravitational energy and some angular momentum, if they fall in middle, in this case, in that way, if they may lose their gravitational energy as well as their angular momentum. Okay, so in order to conserve their angular momentum, they fall at the outer disk or say in the disk in order to conserve their angular momentum. Okay, this way the angular momentum is conserved, and so therefore the other particles start falling in the disk, and their up and down velocity related to the disk average out to be zero. Averages out to be zero. Okay, and so therefore particles keep merging in the disk, and thus they form a disk at the outer of the sphere in the middle. It's very small, and particles usually don't fall in the middle. They fall at the outskirts of the sphere, the disk. Okay, so the next step is how the planets were formed. So the planets form out of the same protostellar disk. In some parts in the disk, there was some clumping of matter in some rings which were relatively in high density. So it started forming like this. You see these planets. Okay, I've written here formation of planets. Okay, so these planets started forming out of collisions of matter. Okay, so it is very simple and very explicable. Now talking about how some planets like Jupiter have high rotation speed as compared to the Earth having very low rotation speed. Earlier I explained this with some theory, but I was proven wrong in the middle by some person. And later, after 2 days, I devised a new thing and searched on internet. And now I come with some mathematical explanation as well as some theoretical proper explanation to suggest you how it did. Okay, if you apply conservation of angular momentum, I1 omega 1 is equal to I2 omega 2. Going by mathematics, it says that rotational speed is independent of mass. Yes, rotational speed is independent of mass. So the equation finally comes out to be r square omega p, that is omega p is rotation omega of planets, okay, is equal to r square omega 1 plus 2 by 5 rp square omega 2, okay. That is the initial angular momentum of the ring is equal to net angular momentum of the planet plus the planet about the center, okay. It comes out to be independent of mass, that's the thing. So if it is the mass which acts, which contributes to the rotating speed of the planets, then what else is the reason for the high rotating speed of the Jupiter as compared to the Earth? Let me tell you, it's this shrinkage factor. Shrinkage factor. Now, how does shrinkage factor play the role? That actually is the same based on the same principle of conservation of angular momentum. The shrinkage factor of Jupiter was very large as compared to the Earth due to the type of material it is made up of. That is, Jupiter is made of huge ball of gas as compared to the Earth made of relatively high dense materials. Okay, so shrinkage factor of Earth was relatively very low. I saw on the internet it was nearly 300 or 400, but for Jupiter it was in thousands, thousands. Okay, that's why applying the angular conservation momentum, you can say that yeah, Jupiter's um, rotational speed must be greater than that of Earth. So this is it. The first session, the first video session of explanation of how solar system is flat. I'll be carrying out the other Sasabar session through videos, and try to make other one if possible. I'll do my best. Thank you.